Hello, Ted.
Hello, Neil.
We are here today to talk about jets. I imagine most of our audience is probably broadly familiar with these, but what we thought we'd do is essentially give a preview of some of the ideas that are feeding into core school as we put that together, and some of the tutorial material that's being pulled into that. And one of the most frequent requests we've had from people about what to cover, like what part of the kernel would they like to know more about, is jetting. So while we're going to be rolling out more scheduling and planning around core school publicly, and people get an idea of what that looks like fairly soon, we decided we'd go ahead, get some ideas about jetting out there, start talking about the how do you build jets, what does the jet dashboard do, what do jet hints look like, and so forth, and walk through this. So, Ted, what's the pitch? What are jets supposed to do for us, properly speaking?
Sure. Well, a jet is something that a knock interpreter can do if it identifies a piece of knock code that it understands and says, I know what this knock code is doing. Let's say it's the add function is adding two numbers together. So the interpreter might see some knock code that it's about to run, but recognize it and say, oh, I know what this code is. This is the add function. And if it recognizes that, then it may have a jet. And a jet is some other piece of code that the interpreter has that's not written in knock. It's just some other code that it has that it can run instead of the knock. And the interpreter knows that it's mathematically equivalent to running the knock, but it knows that its jet is faster. So this happens all the time with, it's not that different from a lot of other things that you might see in computer science, but it's rare to have it be formally specified this way. Typically when you'll want a jet is under a few circumstances. The major one is if you have some sort of hardware that can accelerate this operation. So any arithmetic operation like adding is you can send that to the processor's ALU, its arithmetic logic unit, and run that, right? So then the ALU runs your add function very quickly. It has a specific circuit that does just that, usually a big bank of circuits, right? Let's do them in parallel, all this, lots of hardware infrastructure to accelerate addition. And most other mathematical, arithmetic operations also have corresponding hardware implementations. Sometimes you even have hardware implementations for more complex operations like crypto stuff. SHA-256, not too uncommon to have a hardware implementation of that. Vectorized math operation, all kinds of stuff, right? A modern processor has support for all kinds of specific operations that it can do very quickly because there are specific circuits for them. So a jet is anything that's outside of any way to run knock without running knock, right? It's a way of getting the answer to a knock computation without stepping through that knock computation directly. And instead, the interpreter has some other means of arriving at the answer. And the idea is it's sort of like a jet-assisted takeoff, right? Which is one way that you can get a short takeoff for an airplane. It's also a pun on the word JIT, which is an acronym for just-in-time compilation, which is not what jets are, but that's another technique for taking an interpreted dynamic language like knock and trying to make it run fast. Is to instead right before you run the code, you compile it to machine code. So that's called just-in-time compilation. And there are different strategies for doing that to optimize the code. So Urbit doesn't have a JIT, but we do have jets. And the nice thing about jets, well, there are a lot of nice things about them actually, but one of them is that, and the main reason that Urbit uses them is that it allows a separation of mechanism and policy, right? Where the policy for what answer a computation should have, right? What's the result of running a knock expression? That's specified purely in knock. And so you can evaluate that where the only thing you have to agree on to get the right answer is what is an ordered pair, like what is a cell, right? And what is a natural number, and you know how to compare those for equality and add 1 to them. So natural number is just an integer greater than or equal to 0. And if you as long as we can agree on those two concepts, ordered pairs and natural numbers, then we can read the Nock spec and agree on what the answer to any Nock computation should be. It's very, very rare to have a practical computing system that has that tight of a specification.
How do we know?
And we actually hold to that.
Right. So in practicing, one of the questions I often field about this is, how do we know if jets are correct? Right. This is where people start to wonder, you have a specification in the Nock. Yeah. How do you know if the C code that you're executing actually corresponds to that?
Yeah, I mean, this is the same question of if you have built-ins in Python, how do you know those are correct? If you have primops in Haskell, how do you know that those are correct? If you have if you have a processor, how do you know that the processor is implementing arithmetic correctly? Processors have bugs too, right? So it's that same question. It's basically it's a subset of the question of how do you know that your interpreter is correct? And people generally just don't know that their interpreter is correct. If you look at most interpreters, like the one that's running in your browser right now, V8, it's not like somebody's formally verified that. Not really. Maybe there are little pieces of it that they formally verified, but in general, most practical interpreters have not had any kind of formal verification applied to them, done to the whole thing. There are some formally verified compilers, compiler tool chains, but my understanding is that they have pretty limited uses. So formal verification means you did a proof of some kind. That's what that means, right? It's like somebody constructed a proof that this thing is correct. And those formal verification methods vary widely in their degree of verisimilitude, right? It's very common to say translate the logic that's in C into some other language that's easier to verify that logic, and then assume that the C is correct, which is a pretty big sleight of hand in my opinion. But especially because the hard parts of C are often not writing C, but knowing the environment that C is running in, and knowing things like its undefined behavior, and is there some sort of Unix there's some sort of Unix shenanigans going on, signals and all that stuff. But in any case, it would be good to formally verify jets at some point. And I think that that's actually pretty doable because they're so constrained, right? So this is one of the other things that's nice about jets, is that the other way the thing you can compare jets to are basically intrinsics, right? Compiler intrinsics, or built-in functions. So you can compare them to built-ins, and you can compare them to an FFI, a foreign function interface, right? Because in some sense, this is Nock code calling into C code, right? Like if you run add and Nock, you're not actually running that recursive algorithm the way it's defined. You're calling into a routine that was written in C. You're like jumping. The machine will jump to an instruction that runs that loop that was compiled from some C code. So it is a foreign function interface, but it's a very, very constrained foreign function interface where you're only allowed to jump to a function that implements the exact same thing that you were going to run, that you have implemented in your own language, right? So very different from a traditional FFI, and then it's different from an intrinsic or a primop, a built-in of some kind, because for basically the same reason. Like, well, you also have to have this defined in the base language, right? So the other nice thing about jets is that Nock code doesn't know whether it's jetted or not, which means that different interpreters can have different sets of jets. And this is important because hardware changes all the time, right? Like what hardware we run something on varies, Right? Urbit runs on a cloud Linux machine. It runs on a Mac OS. It runs on a Raspberry Pi running ARM. Right? I mean, even runs on Mac OS is running ARM now too, right? But they're different architectures. Each of these processors has a slightly different set of accelerators. Right? So one processor might have a SHA-256 circuit. Another processor might not. The fact that normal code doesn't know, all right, so the fact that Nock doesn't know whether or not it's being jetted means that an interpreter can examine the hardware that it's running on and say, okay, I have a SHA-256 piece of hardware. So when I encounter a call to the SHA-256 function in Nock, I can actually use that. Right? This is not the case in, say, the browser. Right? There's no way for JavaScript code to access that SHA-256 routine, even if it's there in the processor. Because it's not abstract enough, basically, right? It's not sort of pulled away from. There's a fixed set of built-ins in JavaScript. There's not a whereas with Jets, that set is not fixed. Each interpreter chooses it itself, and you do need almost any interpreter pretty much anyone is going to need some Jets to sort of get the system up and going. But that set can be pretty different. So if you go back to 2018 Urbit, almost the entire Hoon compiler written in Nock, or like written in Hoon, compiled in Nock, was jetted. So there was a C implementation of the full Hoon compiler until about 2019. So for the first 10 years or so of Urbit's existence, it was bootstrapped off of this sort of big chunk of C code that was implementing the same thing as the Nock, because the Nock was too slow. But then 2019, we get right around there, 2018, 2019, we got a bytecode interpreter for Nock. Nock got a lot faster. And then running that C code wasn't really any faster than just running the Nock. So we just ditched it. We ditched 30,000 lines of Jets. That was a nice feeling. And in general, in the future, right, we should really only need Jets for code where you get some kind of hardware speed up, or there might be a few other things where there's some kind of asymptotic speed up that you get from using something other than Nock, but there are very few examples of that. And then also crypto, because you might want a constant time implementation of some algorithm. Right, so Nock doesn't specify anything about timing. So if you care about how long something takes to run because you're worried about a side channel attack that could use that timing information, to exfiltrate data, if you're worried about that, then you have to run a Jet, because Nock isn't capable of specifying how long something's going to take to run. Right, so there's crypto, which is a carve out there. And then other than that, it should be basically just hardware. Now, for now, we actually have more Jets than
LLMs that are running on GPU, specialized contexts and everything. Yeah,
that should just be a Jet. I mean, you and I have both worked on building array systems in Urbit for this reason, and you've done a lot more work on it than I have, but including writing the Jets yourself. But yeah, Jets are a wonderful part of Urbit. If you look at a lot of other systems that have tried to get to a small, tightly specified, axiomatic definition of their language or computing, but then also want that to be used practically, you usually have to make a compromise. And Jets allow us to push that Pareto frontier much further. Like, we really do have a full axiomatic specification of your entire operating system. And we do run that too. Just, we know that, adding two numbers, we can do that with an ALU. We're reasonably sure that that's the same implementation as Nock.
Well, let's pull add up and actually take a look at the way the hinting and everything looks.
Sure.
All right, let me get in here. All right, so I have add. All right, so we're in Hoon.Hoon. And if we look at the structure of Hoon.Hoon, it basically, from the top down, it composes everything and then runs ride to build it. Head tags, and then right at the top we have our innermost core that's running here. This will be defining. Well, I guess this is our innermost core.
Stop you for a second.
Yep.
We don't run ride to. What we're doing here is we're extracting the ride gate. So we run the ride arm from this core that we produce here, but that doesn't actually compile it. It doesn't run the ride gate. We're just saying return the ride gate, which wraps around the rest of the core. Just a minor difference. Yeah.
Okay. And so hoon.hoon has this nested structure of 6 cores from innermost to outermost. And so when you're writing code in the kernel, one of the things you have to keep track of is what is actually known at the point you are at in the kernel. You can't use various parts of Zeus format or like HTML or JSON parsing or something when you're all the way down at this innermost part of hoon.hoon. These things are not yet available. They aren't defined yet. A lot of the parsers and builders and stuff are later on. So this innermost core is, essentially mathematical operations and a few other things. And so what we see when we look at this is, here's our add, is we have this sigfaz at the top. And if we look at the implementation of add here, a gate that accepts 2 atoms, returns an atom. And what it does is it says, there are two atoms that we're adding together. If one of those atoms is 0, return the other atom. Otherwise, decrement the first atom and increment the second atom. So it's a very formal, almost feels like a lambda calculus style operation available to us here. To the Hoon compiler, so I guess before I get into that, so it's sort of obvious why we might want to jet this. Right, this is really slow because this is literally running a loop for every single step in trying to carry out this addition. For the Hoon compiler, we had this hint. What does a hint actually tell Hoon? Like, what does it do in Hoon, and then what does it do for Arvo and Ver underneath it?
You're asking
That's
me?
a question. Yeah, I'm asking you. Like what does it mean to sig? No. What does it mean to sigfaz here? Right? Like, what is that doing?
Okay, so any sig rune, like any rune that starts with a sig, is a hint. And so a knock hint is a knock 11 opcode. And so sigfaz is a particular kind of jet hint for jetting a gate or a door. So something that has a sample in it. And so what it does is it says, if you run the add arm, then the knock formula for the add arm here that's in this core will start by, it is a knock 11 expression. Right, so there's a knock 11 that has the add there. That's the hint. That has a couple sub-expressions. The first one is the sen add there. Actually, there are a couple more pieces to that the sigfaz will expand out to. But anyway, there's some hint information, and then the body that gets, so then that hint is delivered to the runtime, but then doesn't affect the return value of this expression. Right, so the fact that this hint is emitted to the runtime doesn't make you add 2 numbers and get a different value. Right, what's returned from this function is just the result of adding 2 numbers. And so so we run this add arm, and actually I should clarify a little that running the add arm doesn't add the numbers. It returns the function that can add the numbers, right? So it returns the gate defined starting on line 26, the bartiz that says, okay, here's a function that can take in a and b and returns a plus b. So we're returning that function from the add arm. So the way to call add is that you run the add arm and then you replace its sample, a and b, with so its argument with the actual arguments, and then you run its buck arm, which is a piece of code contained inside of that. So it's a two-part thing, right? First, you grab the add function, and then you run the add function. So it's when we're grabbing the add function, right? That knock expression that grabs the add function, which is this add arm here. That's what has the jet hint on it. And this is actually subtle and important, right? So it's a little bit counterintuitive, in my opinion. But there is a reason it works this way. What we're doing here is we're saying, hey, I'm going to return a core, right? This jet hint says, hey, runtime, I'm about to return a core, and its name is add. And there's some other information there, but basically in the hint, which we'll explain in a minute. But basically what we're saying is, hey, runtime, you might recognize this core. And so this core is this add gate, right? So it's a function. It just has one arm, the buck arm. So it just has one stored procedure in it, which it'll run recursively to add these numbers. And it's so the runtime is recognizing the whole core. And then if you go and fire the buck arm on that core, right? If you actually run this function, then because the runtime has already registered this core as something that's jetted, then it knows to run the jet for add instead of just running the knock. Right. So the
do we incur
here, in my opinion, is that we jet whole cores. We don't jet arms.
Right. I agree.
But there is a reason for it.
Do we incur a cost by adding in this check?
Yeah.
I mean, I imagine, almost any optimization you look at it and you say, well, in the current version of the system, that's not going to be a make or break.
Jet matching itself is fairly slow at the moment. And this is one of the big things that the Aries project is working on, is optimizing the jet dispatch. So it'll actually transpile knock to machine code. And in the course of doing that transpilation, Aries will, at least some of the time, I don't know exactly how well it's going to work, but at least some of the time it'll be able to say during that compile time, oh, this is a call to a jet. It recognizes the core at that compile time when it's looking at the knock before it's ever tried to run the knock. And so it'll actually compile in to the resulting machine code, calls to the jet function with direct jumps to that, so that you'll have good compiler, good processor caching behavior, good like branch prediction, that kind of stuff, prefetching sort of thing.
So I realized I told you earlier the example we were going to do was going to be a floating point example. I actually do have an integer example I can use too. So before we start doing that, then let's actually compare this jetted core here, which is this gate, with the jet to which it corresponds.
Okay.
And this U3C code, I mean, how old is U3? This is like deep lore.
Old.
This is really old Urbit. Yeah.
U3 was there before I really got involved with Urbit. So I remember reading U3 in 2016. So it's at least that old. There was a U2 before it, and there might have been a U or U1 or something before that, but I'm not sure.
Oh, okay. I didn't realize that was a version number.
Yeah.
So there, U3 has this. It's this very disciplined, idiosyncratic way of writing C. That's designed to know about atoms and how to manipulate and push atom and nouns around. And so the standard, I guess, even before I get into this, I should look at tree.c. This is where all the jets are registered for the first time. And it's basically just a huge tree of redirects and hashes. And this is where jet registration takes place. Let's see. I don't know.
This is also the hardest part of the jet system to read, by the way. It just looks like line noise when you first look at it. So don't be afraid.
All right, layer one here. It's also not in order. I've noticed this before. It's not in the order you would expect from the other files. So what we have here is we have,
yeah,
it might be in reverse order, but it's
something's
not intuitive about it.
I think I know why it's in reverse order too, actually.
Okay.
And so it's in reverse order because in this part of the code in C here, you have the smaller context of a core actually points at its enclosing context, which points up at its enclosing context again.
Oh, because C builds backwards from Urbit conceptually.
I don't think it's that exactly. I think it's just that.
Well, there's a two-pointer coming back here from the one.
It's some detail of how the jet matching works. That means that you have to point upward. It's like more efficient to point upward than it is to point downward, which is how, in Nock, right, you have a tree and the root of the tree has pointers to the head and the tail, right? And so that's how you think about it in Nock, and it's expressed in the opposite direction here in C. There is a reason for that. I think it's that it's a faster lookup in that direction, but I couldn't tell you what exactly it is. Mm-hmm. But I do remember that this piece of code points the opposite direction, and it's not what you think. Yeah.
So I guess very, very briefly before I jump into that, because we're talking about core structure here, Hoon consists of 6 nested cores, and they're given labels 1, 2, try. I forget what 4s is, pen and hex, to name them as you move out or more from the innermost part. And so part of the name when we register the jet, this is the core for Arvo that basically says here are all the jets registered under 1 that I'm aware of. And then we're actually going to affiliate the name. This name here is the jet hint name, correct? I believe this is where they match.
Sort of, yeah. So they do match, but the way it matches is that I'm pretty sure that the sigfaz sen add expands out to a hint that includes a path for the name of the jet. So the path is it's like a list of adds. So it's and it'll be like faz2 faz add, or maybe it's faz add faz2, something like that.
Okay.
But the name of the containing core, I believe, is part of the jet name.
And that's why I think that ends in the sig sen here. So we have a sig sen that wraps the cores that are going to be jetted underneath it, and that's why, because it's going to be going down that search path.
Yeah, I mean that's right. So the search path, I would say, is one of the reasons it's done this way. But I guess kind of backing up a bit, it's like the system, you can think of it as just matching the whole core, and conceptually that's what it does. But the way it actually does that is that it matches that core layer by layer. So it assumes, the jet matching system assumes that your jetted cores are actually a stack of layers, the way that Hoon.Hoon is a stack of layers, right? So you have this, at the bottom base layer, you just have the constant 139, right? And then you have this core that just says, hey, what's the Hoon version, right? So there's the Hoon version arm, and it returns that constant, right? So now you have one core wrapping, so it's one little, knock one formula in the head of the core, so it returns a constant. Sorry, it's a noc0 formula that returns the tail, right? Does it return the tail? Yeah, it returns the loss, which is the tail. And then in the tail, the value there is just 139, right?
Mm-hmm.
So we should actually print this in the dojo. So I would do a zaptiz. No, sorry, not a zaptiz, just a cast to tar of .hoon version.
Let me get the mic.
So tick tar
dot.
Okay, that's fine.
Hoon version like that as a lookup path.
Yeah. So here we are. Right. So this is .hoon version means the core that contains the Hoon version arm. So that containing core is a pair, like all cores. The tail of it is just the constant 139, which is the Hoon version.
Mm-hmm.
The head of it is a noc0 expression, which says look up slot number 3, axis number 3 from the subject, like from this core, which means look up the tail. Right. So 1 is the whole thing, 2 is the head, 3 is the tail. So it says look up the tail, which is 139. Right. So if you run Hoon version in the dojo, you'll see it prints out 139. Right, so this is the base of the core stack in Hoon.Hoon. Right, is this little tiny core. The next core is what's called layer 1, which has the add gate and a lot of these other arithmetic functions. All right, so that's the first one. Yeah, so .add, that's going to be a little bit larger, right? Because that has all these different arms in it. And if we want to look at so one thing we could do is run, why don't you do hep col add. There we go. So this is the, let's see if I did that right. So what I was trying to do is get it to print the formula, the noc formula that's in this add gate here. Just so that we can take a look at it. And
I believe this is correct because this 9 lookup is going to be looking for deck.
Yep. And then also you can look at, so it starts with the noc6, right, which is an if, and then noc5, which is equals, and then 1, 0, so which is constant 0. So if 0 is equal to 0, 12, which means look up axis 12. Axis 12 is A, right? It's the head of the sample. The sample, which is the argument, is axis 6. So to look up the head of that, you multiply it by 2. So that gives you A. The tail of it is multiplied by 2 and then add 1, which gives you B. So that'd be 13, right? So this says if 0 constant is equal to whatever we have for a value of A, then look up B and return that, which is that what col, right? So what col tis pal 0 A par, then return B, right? And then there's this recursive call with the 9 2 10. 9 2 10 6 means we're going to run the buck arm and we're going to replace the argument, right? So you ever see 9 2 10 6 there? In noc, that's buck pal something replaced something else. So in any case, here's our formula, right? But this is the head of the add core, the add gate, right? So now why don't we? I would say, why don't you just type just add here, so we can get the pretty printer to tell us what's going on. Yeah. So this is actually more, as much as I hate the pretty printer in general, it's useful for this. So what this says is, here it's a description of our add gate, and it's the whole core stack inside of this add gate, right? So first we have 1.otf, which means this is a core with one arm, the buck arm, right? It doesn't have like multiple functions inside of it or multiple things that multiple stored routines. It just has one. And then the next thing here is it says, okay, that's the head, right? So the head of this is just one arm. The tail is broken up into a pair, right? The head of the pair is A and B, and the tail of the pair is another core, right, which has brackets around it, the angle brackets. So that's because this is the actual noun structure of the add core. We have the buck arm in the head, and then the head of the tail is the sample, the argument slot, so A and B. And then the tail of the tail is what we call the context. The context includes everything that's in scope when you define this gate. Right. So in this case, what's in scope is the layer 1 core. Right. So run ..add. Right. So you see that ..add is the core that contains the add arm. Right. So that's the layer 1 core. And it has 33 arms, right? There are 33 functions in there. And then it wraps, so that's the head there. It says 33 arms. There's 33 routines you can run. And then the tail is another core, which has 1 arm. And then the tail of that core is 139. So you know what this is, right? Right. This is .hoon version, right? Run .hoon version.
This is our definitional stuff up here, yep.
Yeah, so why don't you run .hoon version so the viewers at home can see how this fits together. Right? All right, so now we're starting to see this stack here, right? Where, at the very base, right, the bottom right of every core, you're going to see this Hoon version, right? Right, so you're going to see this Hoon version, the core that contains the Hoon version arm, right? .hoon version. So it has this 1 arm, and it has the constant 139. Right? So then we build the little layer 1, arithmetic core that has 33 routines in it, and it wraps around that. Right. So .add, the arithmetic core, stacks a whole battery of arms. It just prepends that battery of arms onto the .hoon version core. Right. And then we have the add gate, which prepends 2 things onto the arithmetic core, right? So it prepends its own arm, right? The actual body, the hep call add, right? Where it does the knock6 or the knock5 to check whether this something's equal to check whether what A is 0, and if so, return B, otherwise recurse, right? So that whole body, like that, the Hoon code that you see inside of the add arm, that's prepended onto the arithmetic core, and in between, you have the default arguments, right? So A and B, this pair of A and B. So you have the add, formula, right? This thing where you're doing the whet call of tispal 0A, right? And then recurse if not. That's the 1.otf in the add gate here, right? So you have that formula, and then you have the A and B, and then you have the context, which is the arithmetic core and all of the cores that contains. So this is the core stack, right? This layers. And the reason it's stacked this way is so that every time you prepend a layer, all the previous layers are in scope. The only way for something to be in scope in knock is that they're in the subject, right? They're actually there inside the core, right? There's this knock, this knock noun that's there, and then any code that runs in a formula can look up anything that's in that knock noun. It can read data, it can run stored routines if they're stored in cores, right? And so in order for like layer 2 of the Hoon, layer 2 does containers, lists, maps, sets, that kind of stuff, and you need to do arithmetic for that, right? You need to be able to like add and subtract and whatnot. So in order to do that, in order to add and subtract, you have to have access to the add and subtract routines, right? Which means they need to be in your subject, which means that your core that defines these map and list and set routines needs to include the core that contains all of the add routines, right? So we're stacking upward and to the left. And because that's the natural shape of Hoon code, the JET system reflects that. So instead of instead of when defining your jet by saying, or defining your jetted core, instead of defining your jetted core by saying, hey, here is this big core. That's not how you do it. What you do is you say, hey, here's the tip of my core, and then I'll tell you where to find the contained core that is my context that is also jetted. And so each time you prepend a new core into the stack, all you have to do is say, hey, here's the new one, and you point at the one that you've already defined. And this is also why you see on the right here in the C code, you say that, why don't you look for layer 1 here, right? Actually, this is layer 1.
This is layer 1.
So here are all the cores. Yeah, so here are all the cores that contain layer 1 in their context, right? So add is one of them, right? We've seen that, right? Add has the layer 1 core, it has the tail of the tail, right?
And not everything is jetted too, which is worth noting. Like some of these have jet hints and they are not jetted in practice.
Mm-hmm. Yeah, they don't need to be, probably, or nobody bothered to write one.
Yep.
Actually, that's a pretty good one, right? Max. You could write a jet for Max.
I wonder if it's not fast enough. Oh, you mean like right now? Yeah, we could.
Yeah. Make a pull
well,
request.
Why not? So what this would look like in practice then is we are telling Arvo via this core that there's a function and there's a hash. So there's a label, there's a function, and there's a hash. Offhand, I don't recall what 7 and 0 are doing for us here, and I've never messed with them. So
okay, so
I've never
I
touched
don't remember
them.
what 0 is, but 7 refers to the slot of the context. So this is what I was saying when I say when you write a jet hint, right? When you write a jetted core, you say, here is this core, like here's the root of it.
Mm-hmm.
And then you give it a slot number to say, here's where you can find my context, like my parent core, within me. And that all has to also be jetted. So let's take an example here, right? We have the 141 add A, right? Actually, wait, no, that's okay. That's not what I meant. All right, we have the 141D, right? This U3J core here, right?
This, yes. Mm-hmm.
Yeah, so we're saying here's an entry, and this is we're calling it the 1. This is the layer 1 entry. 140 is the version number here, which is actually the old one. We have 139 and 140 next to each other.
Yeah, that's always been kind of an interesting. Yeah, here's the 139 stuff down here.
Yeah, but before we get into that, let's
anyway, yeah.
Sorry, I should not have digressed, but here we're saying, hey, here are all these here's this array of cores that contain the layer 1 core inside of them. And so we say, okay, here's the add. This add gate contains the layer 1 core, and it contains the layer 1 core at axis 7. So the tail of the tail. So we're saying that within the add gate, the layer 1 core is at axis 7. It's the tail of the add gate. Contrast this with the layer 2 core, which is defined in line 2095, which says that the layer 2 core contains the layer 1 core at axis 3, which is just the tail. So the difference here is that the layer 2 core is a stateless core, unlike the add gate. The add gate has the sample slot, right? It has this argument slot, A and B, that you can swap out and replace with 3 and 4, and then you can, when you run the buck arm of the add gate, then you get 7, right? Because you've replaced those arguments. So there's a slot where you can where that's all nouns are immutable, but effectively you're treating that slot as mutable. And that shows up in the type system as well. The Hoon type system will say, yeah, that's a mutable slot. It's writable if you have some part of a core that's considered writable, then that's what that means. Is like you can write different values in there. You can, instead of 0 and 0, which is the default, you can write 3 and 4, and that won't change the type of the core, because the Hoon type system understands that kind of core is a gate that's intended to have those pieces of it swapped out. So then when you run the buck arm, you actually get the result. So that has a writable slot here, the sample slot. So the add formula, right, the formula in the add core, hep col add, right, that body of the add gate, that has the sample slot in between it and the context, right? So we have three, so the add gate is a triple, right? And we have, the actual, buck arm, the sample slot, and then the context, which is the containing core, right? The context, the other core that we're containing, right? The layer 1. However, for layer 2, the layer 2 core it doesn't have a sample slot. It's not a gate. It's just another collection of routines. It's another library, right? Just like layer 1, right? There's no sample slot. You're not passing an argument to layer 2. Layer 2 defines a bunch of functions that each of which you can pass arguments to. But it itself, layer 2 core itself, is just defines a battery of routines. There's no argument that you can pass into that. And this is true in general for bar-sen cores, right? So you have a bar-sen rune that says, hey, just slap some routines, prepend those onto, whatever subject you had before. A bar-tiz defines a gate that slaps the sample and then slaps the formula onto there. So for the layer 2 core, we have a bunch of routines in the head, and then the tail of the core is just the layer 1 core, right? So why don't you write what's something in layer 2? Why don't we look at layer 2 so we can
like Biff.
Yeah.
Biff is in layer 2.
Great. Okay. So dot.biff is the layer 2 core, and we see that the layer 1 core, which starts with 33, right, is right there. So that's the tail. So the head of the layer 2 core is just 139 different routines, and then the tail is the layer 1 core. There's nothing in between. There's no sample slot. Because there's nothing in between there, when you define the layer 2 core, we specify in the jet hint that the location of the context core within the layer 2 core is axis 3, the tail. And we can see this if you look at, so if we look at the definition for the layer 2 core in Hoon, we should see this. So we should see the sig sen there that puts the hint on it. So why don't we look at that at layer 2? Yeah. Okay, so now it's time to go through how to read a sig sen rune. I think we now have an understanding where this will make sense, because we can see what happens to it on the right side of the C here, right? So line 376, right? We have the sig sen rune. So we say here's layer 2. It's called 2, right? Sen 2. That's the name of that's a string, right? That's the name of this core. And then there are two other arguments, and then the core itself. The last argument, sig, is a set of jet hooks, which is a bit of an advanced topic for jetting. But what that allows you to do, if that's not sig, which is null, then that allows you to say, here are a bunch of arms within this core that we want the runtime to know about, so that jets within that core can call those arms. Can call back into knock. So that's an advanced feature for what if you have a core with a bunch of arms? You want to write some C code for a few of those arms, but for the other ones you want to leave them as knock, and you want the C code to be able to call into the other arms. All right. So if you want to do that, then you have to specify what the other arms are, right there where there's the sig here. So very rare that you need to do that. So I wouldn't worry about it. But that's what the sig is for. And if you want to see an example of this, you can look at the ut core, which actually does define some jet hooks rather.
Yep, there's a whole
Yeah,
whole
right.
table
So here you
here.
see all these arms. Yeah. So and there's sort of a funny syntax where there's a tis before and a tis at the end if it's not sig, right? So it's a very funny looking rune if it's not sig there, but almost always it's sig. So let's go back to 2 because this doesn't have this. So all right, so we've got this jet hooks, that's empty. We have the name 2. In between them we have lus plus, right? So what that is that is a wing. Right, so this is a Hoon expression that gets compiled to a tree slot number, an axis. So lus is axis 3, the tail, right? So what this is saying is, so the Hoon compiler sees this, and it compiles that to axis 3. You can also, you don't have to put a lus there. I think you could actually put .add there as well.
Okay, that would make sense.
Right, because if you do like in Dojo, do zaptiz of .add. Right, so zaptiz means compile. Zaptiz. Yep. .add.
There we go.
Right. So this compiles to a noc0, right? It says, which is a lookup, right? It's like we're going to look up a slot. So this is looking up slot 1023. So that .add is a wing, which means anything with any Hoon expression that's like foo.bar.lus1.lusgal.baz, right? Any thing with a bunch of dots in between, that's a wing in Hoon, and so that gets compiled to a single slot lookup. Yeah. So you can see that's the AST that results from parsing this Hoon, right? So if you just say add, then you can do a .add, and it'll be wing of. You want to do the zapcom to show how the .add gets parsed. Yeah, so that's a send-tis. And then the send.y1 means like grab the whole subject, right? Grab dot, because dot is axis 1, right? So that send.y1 means grab axis 1, which is the whole thing. So this is saying, so this is a send-tis expression. It's a little funny, but you'll see it. You see it does actually compile down to a noc0.
Yeah, they're all okay. They're all going to behave that way. Okay. Yeah, it's interesting that it doesn't parse as a wing path the way that other wing expressions do. But
yeah. Right. The so in any case, you have to put something. You have to put some expression there where the lus is that becomes an axis, and then that axis is used to match, right? So because the idea is you've already the interpreter has already seen the layer 1 core, right? By the time you're running this expression that returns the layer 2 core, the interpreter has already seen the layer 1 core, and so then when you refer to the layer 1 core inside of the layer 2 core, it knows about it. And so you're building up this stack of these layers in the interpreter's mind, right? So the interpreter is learning about this, and that way, this 2 here, you don't have to, when you write this in Hoon, right? Some of this is for the programmer convenience in Hoon, so that when you write this, you don't have to say, hey, this is actually, the name of this jet is 21139 or K139, right? That's not the jet name. right? We just have to remember 2, and then that path, that list of names gets constructed in the runtime, right? So it understands that because it's pointing at the other ones, that it can just prepend 2 to the 1 K139. So in general, like the way that all this jetting stuff works is based on like adding one more layer to a core.
Okay. This makes sense.
Cool.
The less bar stuff doesn't currently do anything, does it? The chapter labels.
They do affect the layout of the battery. So the arm will end up at a different axis based on that.
Okay. There we go. Okay, we're back around here then. All right. Okay, so this gives us our core structure over here. And then with, for instance, add, what this means is we have another reference up here that includes a hash as well. This is going to be the actual entry point function for add. This is where the sample noun will get sent. This is a flag that tells it whether or not you have verified the jet. And if you turn this to C3N, then it should, it's unclear to me if it runs both and compares and errors if they're different or exactly what happens there, but it's considered an unverified jet.
Sounds right.
When that's a C3N.
I think
so. It actually does run both. Okay.
I think so. I'm not totally
Do you know
sure.
do you know what this is? It's another part
No.
I've never touched. So okay. These are kind
is
of,
it always that? Do you see any?
No, I've never.
Oh, I think
that's one that I've never changed. So.
Yeah, but I'm wondering if there are any others that are not, any of them that are not .2 but dot something else. Like, can you search for, quote dot, and then I can scroll through and see if any of them are not 2. I have a guess about what this is.
Yeah, I don't see anything that's not.
So my guess is that these are.
Yeah, it's the same. Yeah.
Is that this saying? This is the arm at axis 2, right? Because almost all these are gates, and so you're going to be running the arm at axis 2 within the core
battery.
Jetted.
Yeah. Yep.
Yeah. Right. So because a gate that just has one arm, that arm is always at axis 2. Some other kind of core, there's a bunch of arms, a bunch of routines in them. Those can be at different axes. They're all within the head, but they won't be at axis 2.
So in practice, no one's
almost
ever
everything
calling anything else. But in principle, you could.
Well,
jet
I don't know. I mean, I would look for UT actually, because I think UT has some arms that aren't gates.
It's still referring to 2. Yeah, every one of them that has it still refers to 2. Yep. So right. I know, I remember when I was first looking into this a couple of years ago, I did see a few places where there was a note to the effect that you could specify something differently and get a different behavior, but everything in the system does it this way. This seems like one of those instances. Okay. Let's see. I guess I want one add. There we go. Okay. Now, what does this hash come from? I don't think these are verified right now either. They're included, but I think they're not actually verified.
Yeah, there was an idea a few years ago that you would use, that the runtime would have a hash of the either of the battery or of some static part of the core, or maybe of the whole core, and that it would use that to verify that it was matching the right thing. And then my understanding is that we don't use that. and that there is no verification in that way anymore.
Okay.
And so there's a way of writing these where you don't specify a hash, I believe. Something like no hashes or something like that.
Okay. But looks like pretty much everything in the system, at least this deep in the system, provides it at least. All right, so now we're to the jet instead of the jet registration. U3WA add, which is, in this case, the jets are organized A, B, C, D, E, F by core depth. So this A refers to everything in core 1, B and everything in core 2, and so forth. This typically has 2 or 3 functions inside of it, depending on the particular structure. Q and W are typically there. K is not always there in my experience looking at these. But this is the entry point where we're actually going to run code. And so this receives a noun named core. And this is, let me adjust it a little so it fits on the line there. It's a little bit more legible. This means that we are receiving a noun and we need to unpack it into the particular arguments that we are working with. Do any sanity checks on those, and then if we fail to crash, essentially bail is our crash, then we will pass those particular arguments to the calculating jet function. And so our checks are, first we're going to try and unpack the values that we expect, and in this case we expect something at sample axis 2 and sample axis 3, and we're going to write by reference into A and B as U3 nouns.
Yeah, it's kind of a cool pattern, right? That we can do.
Yeah, it works fine.
This U3 mean is it's a destructuring. We're saying, okay, we've been passed this down, and we want to grab, take sample axis 2, like axis 2 within the sample, meaning the head of the sample, which is A, right? We want to assign that, extract that value and have, our local variable A point at that, right? Or contain that 32-bit noun reference. So we're going to overwrite our local variable A with that. And then you would do the same thing for B, which is at the tail of the sample. And if you can't do that because those axes don't exist within this noun, then crash. U3 mean means crash if you can't extract. Well, is the crash? I guess it actually just returns no if you. It'll
return a no, and then it'll crash here. Yeah. For those who haven't, I was going to say, for those who haven't looked at U3 before, the third letter are things like they refer to these files over here on the left in noun. Like R is retrieve. These are things that unpack nouns into C style variables that we can then manipulate. U3N would be knock functions. U3I is the other one that R and I get used a lot because I is imprison. R is retrieve, turn it into a C style value, do your calculation, and then before you return it, U3I, you imprison the value back as a noun, and then Arvo knows where to redirect this afterwards. Let's see, U3, UD. So these are verifying type.
Just checking whether they're atoms.
Right. And then it's checking that A is not 0, which seems superfluous here, but okay.
No, here's why.
I don't know why you would crash if it's 0. Okay.
It's because look at the knock. It's subtle. This was fixed a while ago. It's interesting. It's an interesting example of a something that used to be a jet mismatch, if I remember right. But just not the knock. Sorry, look at the whom. Just scroll down a little bit to show the add gate.
Yes.
So if you look at how this works, let's say that B is a cell. B is not supposed to be a cell. It's supposed to be an atom, right? It's supposed to be a number. Mm-hmm. But what happens if you take the knock for this add gate and you run it in an untyped way, right? Hoon won't let you do this. Hoon won't let you pass it won't let you
A
pass
cell
a
for an
cell.
edit.
Yeah, it'll say that's a type error. It's generally sane compiler. Hold on, I need to sneeze. Okay, but the noc that's compiled from this doesn't check. So you can actually try this in the dojo. We'll do it in a second. But basically, what happens if you look through this, the code just says look at A. If A is 0, then return B. It doesn't bother checking whether B is a cell.
Ah.
And so we actually need to have the C code for the jet replicate the subtlety of the noc, or else you could have the jet
does the kethep not
crash
get
when the noc
reflected?
doesn't. No.
So
That's just a type
kethep
edit.
doesn't show up in the noc.
There's nothing in the
so
noc.
that's pure Hoon
Right.
side. Okay.
Yeah, ketheps don't show up in noc. Ket losses also don't show up in noc. So you can try this. You can do a slum add 345.
What's the slum syntax?
Sorry, add slum. You can just pass them all as args. Because slum is a gate, but it takes in another gate and then the arguments. So this should crash. Yeah, but try slum add 045. And this will actually return 45. Right.
Okay.
So it just for reference, you do slum add 3.4 and you should get 7. So slum means run a gate with an argument, but untyped. Just run raw knock on it using .tar.
Mm-hmm.
Right. So you could also do .tar of let's see. No, you don't want that. Well, it's okay. You've got to put the subject in first. So we could do no, that's the gate. That's the core that contains add.
But that'll be our subject.
So what I would do here, I think.
Won't it?
No, we want the add gate. So you want add as the subject, right? Which will run the add arm.
Okay, we're constraining.
Okay,
we're constraining it right there. Okay.
Yeah, and then you can say. So the formula here is 10, 6, 1, 3, 4. And then let's see, there's some brackets in there. But then and then we need to do 9201.
I don't suppose I could.
So do
see an example of what that's supposed to look like.
Yeah. Okay. So there's 6, and then so we need to put 6. We need to put a brackets around 6, 6, 1, 6, 1, 3, 4 should have brackets around it. Right. So that's saying at axis 6, it's just saying replace axis 6 with constant, which is return constant means 1 means return constant, pair of 3, 4. Mm-hmm. Right. So we're replacing axis 6 with pair of 3, 4. And then we do 9201, which means so 01 means identity, return the whole subject. Oh darn, why didn't this work? Here we go. Getting
right. I mean, we terminate with these here. Yeah.
Because I did it in the wrong order. It needs to be 9-2 and then 10 blah 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 01. So get rid of the 9-2 at the end there. Leave just 01. Yeah, try that.
Okay, there we go.
Yeah, there.
Yep.
Yeah. So what this is saying is, you got to read it from right to left, right? So you start with the current subject. 01 means identity, right? Return the whole thing. Return the whole subject. Mm-hmm. So return the whole core, which is the add gate, and then we're going to do this knock 10 operation where we replace axis 6 within the add gate with the pair of 3, 4. Right. So going right to left, now we have, this add gate with the sample replaced with the actual arguments, pair of 3 and 4. And then once we have that, then we run 9-2, which says run the buck arm on this modified core. See, why are we doing this?
Because of this.
Right. Okay. So now replace it with 3, 4, 5, and you should see that this fails. Right, because this is trying to add 3 and pair of 4, 5, but 3 is not 0, so this actually crashes. But yeah, as you just showed there, if A, the head of the sample is 0, then right, it'll actually it'll run anyway, right? Because the knock isn't checking. In general, like the knock output by Hoon code doesn't include type checks, because Hoon expects that the type checks are done at compile time, right? We do type erasure from Hoon. Hoon, like most statically compiled,
right. It doesn't carry that
statically
information.
typed languages. Yeah, the Hoon compiler does type erasure. So the resulting knock code doesn't mention anything about types. It just knows where things are, right? This is why knock is amenable to optimization, right? This is why the Aries project can exist in the first place. You look at all this stuff, it's all static, right? Axis 2, you can look at that in the knock formula, right? Whatever comes out of the Hoon compiler, you can look at that. You don't have to run it. It's gonna grab that particular slot. You can't grab a dynamic slot in Hoon. This often confuses people when they're first learning about Hoon, but it's a very statically typed language, right? So which arm you're going to run, axis 2, right? The buck arm. Which slot you're going to grab, right? Axis 12, the head of the sample slot, right? Hard coded in the knock, not dynamically computed at runtime. Unless you do a knock 2, which is dynamic when unless you're doing this .tar rune, which emits a knock 2, very dynamic. You're dynamically constructing subject and formula, but you very rarely do that. So yeah, so anyway, the knock doesn't have all these type checks. So here, that's what and A is not 0, right? So we only fail if A is not 0, because if A is 0, then we're fine, right? We just return B. Yeah. But yeah, so but this is a good example here, the U3WA add, because this is saying, it's a good example of this two-phase jet running system, where first the interpreter just passes the whole core to the jet. That jet first extracts the sample and does whatever validation it needs to do. It may need to validate things that are not in the sample, but that are in the sample of the context core, right? So like get by, for example, it has two different writable slots, right? So it has the actual map that you're going to perform a lookup on, and then the key that you want to use for that lookup. And those are two different writable slots within the noun, because there's the by core, which wraps the map data structure. So that has the map data structure as its sample, which is writable. And then you have then you have the get core, which wraps around that, and that has the key as its sample, its writable slot. So now you have both of these arguments, right? So this, so the jet for get by is going to have to look at both of those and actually, extract. So that's how it's going to extract the function to run there. So then once we and the actual arguments, and it might have to do some other validation as well. So anyway, we do this validation and destructuring, find the sample, and then once we have the sample, the actual arguments, then we call U3QA add instead of U3WA add.
Yep. And
then U3QA add does the actual meat of the logic
with our actual U3 noun values. Yeah. So now it's probably worth addressing what is a U3 atom here, right? Like what is this type? We're carrying this around.
It's a soft alias for noun, right? Like it really just means a 32-bit noun slot, but where we're expecting it to be an atom. So it's written in C, so it's kind of a soft type system. It's really just like a width system in C. Right? If you wrote this in crab language, then it would actually have static guarantees that that it is actually an atom.
Yeah.
But in C we don't.
And so
and there are tricks
when
you
we
can
say
do in
this,
C to make it that way, but we don't bother.
so when we say that this is an atom, the first check that we're doing here, you'll see this throughout jets when you do jets, is right at the beginning, people check, is it a cat or is it a dog? Right. And there's also this this little weird macro we can talk about in a minute as well. But so this is let me, I think I actually have
It's one of my favorite parts of the names in the system, actually. So cat is direct
cat
atom,
or a dog.
and dog is
find...
any kind of indirect data structure, right? So you want to look up the definition of nouns. That was when you want to show people.
No, well, I have there we go. Okay. So a cat. So, all right. So every atom here, everything that's a U3 noun or U3 atom is a 32-bit CUN, whatever. And if it's a cat, it has this structure.
Calling it a uint is even a stretch. It's 32 bits. It's a 32-bit,
And if it's a dog, that has this structure here, which means basically you can look at the head.
You sure about that?
And you can tell.
It's not just one. I thought dog was any indirect. Is dog specifically a cell? Specifically?
Well, a dog is any indirect, which means it's a pointer. Right. A cat is direct, which means it's the actual value.
But then you don't know
this.
But then you don't know the second bit, I don't think.
Well,
the second bit is either 0 or 1.
My understanding is the second bit,
an atom or a cell.
Oh, my understanding was the second bit was always set. And that Y was atom or cell. That bit 30 was, or bit 29 was atom or cell. So this is dog. My understanding is this one's always set.
That might depend on whether you're running a 2 gig or 4 gig loom.
Right. This is the sort of thing that might have changed based on loom structure, but it used to be that was always fixed. And then Y is this an atom or a cell? And then the X's were the loom address for the pointer.
Yeah. Oh, we got some questions here, by the way. Or just one. So an atom that's bigger than 32 bits is a dog, asks John Hyde.
An atom that's bigger than...
Well, yeah. I believe a dog is any noun that's not a direct atom. So a direct atom is 31 bits or smaller. Because that top bit is used as a tag. So if the top bit is 0, then it says, okay, we have 31 bits left to define an integer, an atom, in the rest of these 31 bits. Otherwise, that tag bit is a 1, which means that the rest of the 31 bits are used to point at some other value within the loom. So you have a 31-bit pointer, but it's actually a 30-bit pointer because the next bit, or maybe it's the bit after that, depending on sort of which version of array you're looking at, is 1 if we're pointing at, or I don't remember which is 1 or 0, but if we're pointing at a cell, a pair, then it's 1. And if we're pointing at a large atom that doesn't fit in 31 bits, then it's a 0 or a 1. I can't remember which is which, but right. But that next bit determines whether you're pointing at an atom or a cell, which is nice because in the Noc3 opcode, it checks whether a value is an atom or a cell. And so you can just look at the first 2 bits of that 32-bit slot and resolve the Noc3 opcode without having to pointer chase, or you don't have to actually fetch the data that this thing is pointing at in order to answer that, which is really nice in some cases because maybe fetching that data, maybe that's not in your processor cache and you have to load it from RAM, and that would slow down the whole thing, right? So, so it's a nice little optimization there.
So we have to check basically, are these direct or not? Because if they're
Yeah.
direct, it's really easy. And we just re-imprison the value as a one word with value and pass it back out.
Wait, where does it actually add them here?
This is
Return
the
U3I words. Oh, I see. Yeah.
line 14.
Right. So we just run A plus B like in C, right? Basic C addition. We don't have to do any, large, big int kind of stuff.
Right. This is the other case, is the big int.
Yeah.
So this is flipping our logic from Lubian to C style logic. So you'll see this single cab or double cab wrapped around various expressions, because you have to keep track if you're in Lubian or Boolean space.
Yeah, the way it's more common I've found to see just, and I find it a lot easier to remember, to just, if you're doing anything with, with like U3, then whenever you have a conditional, check against C3Y or C3N, yes or no. And that way you don't have to remember kind of like which thing you're in. Like, I don't know, it's actually the same as the cab, the underscore, but
right, that's a macro.
I just
cab and double cab are macros.
Yeah, but if it'll get compiled to the same thing. LLVM is smart enough to understand, like, oh, you're checking if it's equal to 0 or equal to 1, and you can just flip or I don't know what they compile it to, but they'll compile it to whatever is the right thing to compile it to.
Yep.
John Hyde further asks, is it called a dog because a pointer is a kind of hunting dog, or because it fetches? It could be. I hadn't thought of that.
I choose to believe this.
Exactly. So this is I think you've hit on the right way to learn these kinds of things, which is make a mnemonic that you like, whatever is evocative for you, and stick with it. For me, cat and dog.
Than dogs.
Exactly. Yeah. Same. Yeah. And then I believe the kinds of dog. The other thing is that there's if you have a direct atom, I think that's a pug, and an indirect atom is a pug, and a cell is a pom, which is of course short for Pomeranian. And so it's like, okay, well they're pugs and Pomeranians, so those are dogs. And the fact that there are two kinds of those is because it's indirect. There's only one kind of direct thing, right? So you can further use that to cement the constraints here, so that you remember which is which. I mean, whatever, right? We just wanted a short name. Cat and dog are both 3 letters. Pug and pom are both 3 letters. So
Hoon uses 4 letters for everything, and U3 uses 3 letters for everything.
Well,
to a large
not everything,
extent,
right? So for variable,
but it's sort of its preferred bias is to 3-letter.
Okay, so variable names are 3-letter. Type names are 4-letter. U3 noun is 4 letters. U3 atom, U3 cell, U3 weak, U3 none. Right.
But those are really Hoon types that we're spoofing here.
No, even when you just define structs in the IO drivers, you also use 4 letters typically. You don't have to, but it's common. But 3 letters are usually reserved for local variables or field names within a struct. And that's the same convention that we use in Hoon, right? So type names are 4 or more. Locals are 3. There's a lot of mirroring between Hoon and Var. Like once you get, this is part of like, I don't know, my experience with core dev is like, Var makes a lot more sense once, like Hoon made a lot more sense to me once I understood Nock, and Var made a lot more sense to me once I understood Hoon. Because they're very similar. They use a lot of similar patterns, not just the naming scheme, but even just like the feel of Hoon and Nock is very similar to C in a lot of ways. There's this similar kind of like lack of squishiness. Is it like the term that people use almost always, and they do a bunch of Hoon programming and then go back and write some Python or some JavaScript or whatever. They complain that the Python or JavaScript feels squishy. And I know exactly what they're talking about. And if you do enough Hoon programming, you'll feel it too. C doesn't feel squishy in that same way. It has other problems, but at least it's not squishy.
Yep. All right, so there's our check, wrapping our value back up. U3K, is that a ref count decrement? What's U3K? There's a lot of 3-letter
It's an increment.
aliases. Is that that's an increment?
That means,
okay.
yeah, that's increment the ref count. Gain, yeah, gain, and U3Z is lose. So this is gaining a ref count versus one. Yeah. And I think that's from signal processing somewhere. Like K is gain and Z is lose. Maybe you told me that actually. But that's yeah. Anyway, there's some reason it's that way. I don't remember what it is.
Okay. Otherwise, we have to deal with big ints with the GNU multi-precision library, which means we have to unpack things. So there are special values built in for that. Do a special addition operation on top of that, which is assembly style. So we're specifying the 2 values and the destination all together, and then clearing one of them and then imprisoning the other one and sending it back out. So straightforward within the constraints of now we're working with big ints, which are a bit odd to work with. This is really common in jets where you have to check for direct or not, and you don't want to forget the or not scenario because a lot of your testing may be taking place with relatively small numbers that aren't going to trigger this case, and obviously things will break if you don't get ahead of those. And a lot of these have the U3K version as well. This is only referred to there. Yeah, I don't know if.
Okay, so I'm not sure about this, but I think the difference between U3K and U3 was it Q that.
I mean, it's called by U3K.
What? Yeah.
U3Q is
so
called
the only
by
difference.
K.
Right. So the only difference is in the reference counting semantics.
Mm-hmm.
So one of them uses the standard transfer semantics. That's the default for most of var, and the other uses what's called retain semantics. Transfer semantics means if I pass you an argument, I'm relinquishing all responsibility for managing the memory that I pass you. So if I pass you some noun, you're responsible for either holding onto that noun in some persistent way and not losing the reference, or decrementing the ref count so that it gets freed if there are no other references. Right. So transfer means I'm transferring ownership of this ref counted noun to you, to the callee. And that's standard. It's the same idea as Rust, right? If you've ever worked with Rust ownership semantics, it's the same thing. It's just we don't have enforcement of it because it's in C. And even if you did it in Rust, would help in a certain way with this ref counting stuff, but not completely. So they do it in a different way, but the basic idea of ownership of values is still the same. So typically in var, if I call a function, I'm transferring ownership to that function. If that's not the case, and you write a function that doesn't sort of grab ownership of the arguments that it's passed, then that's called retain semantics, where the caller retains ownership of that noun. So jets, I believe, are actually usually retain, not transfer, if I remember right.
Yes.
But we can check because we can look at U3K versus U3Q, and we can derive the correct answer from looking at that, right? So U3K here calls U3Q, and then U3Z is A and B, right? So which means it's decrementing the ref count on A and B. So we can infer from this that U3Q uses retain semantics, does not decrement the ref counts. So it's not taking control, it's not taking ownership of A and B. And then, but U3K, which is the one we're looking at? I'm sorry, I'm good.
I just scrolled up. Yeah, we're looking at U3K.
yeah, so U3K does decrement the ref counts, which means it is taking ownership, which means it is using transfer semantics. So U3K is for transfer semantics, U3K is transfer semantics, U3Q is retained semantics. Mm-hmm. And considering that U3W, which is the one that takes in the core, considering that calls U3Q, not U3K, that means that U3W is also retained semantics. Which kind of makes sense, right? Because it's like the interpreter is sort of delegating here to the jet system and saying, hey, jet, run some stuff. But the interpreter isn't transferring ownership of the core to the jet system. It's letting the jet system sort of borrow it, right? And then the interpreter is retaining memory ownership of that core. So that kind of, I don't know, intuitively that makes sense to me. And so you could probably express that in a different way, right? You could have the interpreter use transfer semantics, but then I think what would happen is you'd end up incrementing and decrementing ref counts all the time where you don't need to, right? Because
so this makes sense.
Typically the core isn't going to be deleted afterward.
This makes sense from the perspective of, if I search U3K functions, they're turning up in Arvo, not in the other jets. So when Arvo wants to do something in U3 that relies on this, Arvo is going to use the U3K semantics.
Arvo?
Yeah, like serial and, var. Like when non-jet var is using U3, it is going to use the U3K semantics manifestly, and the jets are going to prefer not to, generally speaking. But I mean, you'll run into
the reason
K
to
and
use
Q in both places.
Yeah, the reason to use transfer semantics in general is that it's easier to keep it correct, right? Because it sort of matches the intuitive notions of like, I'm passing you this value, right? Okay, it's like, now it's your problem. And it leads to more concise code, I think, often, right? Because if you're constructing a noun, for example, and you have a bunch of little nouns, you want to construct a bigger noun that includes all of them. When that construction function has transfer semantics, then you have all these little nouns, you pass them to that big function, you get one big noun out, and now that big noun is how you manage the whole thing. You don't have to separately go and delete. You don't have to U3Z, then lose a reference on all of the smaller nouns just in order to build the big one. Mm-hmm. Right, and that's just one example. But often, you're doing something where you have some intermediate variables, and those are nouns, right? Like intermediate values of some computation, and typically you want that to be consumed by the next thing that it gets passed into, the next function it gets passed into, right? So being consumed by default is transfer semantics. The downside of transfer semantics is that you're incrementing and decrementing ref counts more. So there's some performance penalty. And that the amount of that performance penalty varies widely depending on what you're doing.
Yep.
John has another question. So if A is a cat and B is a dog, it's fine to just wrap them both the same way? I'm not sure what you mean by wrap them.
He's talking about, let's say A is a cat and B is a dog. Whatever's happening in U3R is doing the check on, does anything fancy need to happen with GNU MP, libgmp or not?
Yeah, so I think the answer is you don't wrap them both the same way at the lower layer, right? So this U3R MP function is saying, hey, take A, which may or may not be a direct atom, and convert it into A cab MP, which is this big num struct type, right? So it's saying, so that's the conversion there is encapsulated in this function, so that once you so this says no matter what kind of atom A is, make a big num out of it. And so sort of internally it checks if it's a cat.
Yeah, that's what it's doing on the left here. So, all right, do we have other questions? Okay, I think we're pretty good there then. Okay, so we said a minute ago, let's add max. So let's add max. I've already added a line down here. Max is already, the nice thing about max is that max is already jetted here. But if I wanted to jet it, the only thing I would have to do over here is add a sigfaz and then a label, and then make sure that it's under a sigsen tag for the whole jet matching path. So over here, I've added this registration. I will simply copy this and change this to max, this to max, this to max. I'm going to leave the hash alone because they don't mean anything right now. All right. I would add a file over here. It actually doesn't have to be a separate file. It just has to be linked, compiled and linked properly so you can actually find it. But it's conventional to leave separate files for everything. So let's just take whatever's in greater than and use that as a basis for max. How do I do this in? Okay, that's close enough. Don't use VS Code enough here. All right, so there's a max. All right. I'm going to throw away, well, I can leave a K in because I think it'll be straightforward. So let's trace our logic here. So we're going to come in here. We're going to have an A and a B. We're expecting something at a sample 2 and a sample 3 because max is, we're also writing it as a binary operation. So there's not a lot we need to change to make that work. Just need to update what it's pointing to. These are defined for most of the common sample locations for standard cells going in. You can definitely like when I was building the linear algebra library, I ran into some addresses that were not included in whatever these variables or macros, wherever they come from, are. So there's an alternative way to specify the sample by address if you need to, rather than this shorthand. All right, change that.
You could just put 12 and 13 in there. It would be fine.
Okay. Yeah, I don't remember how I did it anymore, but all right, so we'll do a max here. All right. Now, if it's a cat, okay, fantastic. All right. So we're not returning a Boolean out of this, or a Lubian. We are returning which of these is greater. Now, conventionally in C, I've always seen this done with the macro. The pound define, I guess, am I doing max or min? I'm doing max. This kind of thing. And I could copy paste it, but
I think we went the opposite. That's min.
Yes, that's min. Okay.
Super easy to mess those up. There's a great bug there's a great bug fix from Joe a few years ago. I remember there's a pull request, and it was entitled "On the Nature of Quantitative Comparison." And it's like min versus max. There's some part of the code where somebody used the wrong one.
Yep.
They fixed it.
All right, I actually want to throw away both of these comparisons. they don't add anything to what I'm doing here. All right, now we're to the little bit dicier part here. Should be able to leave most of this alone. This is something else that in my experience with writing jets practically, you're working a lot from models and using boilerplate, and you don't need to mess with a lot because there's often like one part that's doing something specific that you need to change here. So
That
there
being
is a
said,
comparator.
know exactly what that stuff is doing if you're writing a jet. Don't just
Yes.
copy and paste blindly. If you cargo cult and make a PR based on cargo culting, I will be very upset with you.
Okay, so our comparator here is built into MPC, which is GNU MP. We compare these, and instead of returning a Loobian or a Boolean, we're going to return.
Yes, I think this is the right direction, right? Because
yes.
What were we taking this from? Greater than? Greater than equal?
We were taking this from greater than. That's why I chose greater than.
Well, okay, so here's greater than 0, but what if they're equal? I guess it doesn't matter. We can return either of them. But actually, it does matter, I think, because we want...
It returns A if they're equal, but they're equal.
Yeah, but there are different memory implications here, right? Like, they're not... Like, basically, if I were going to run max...
Well, no, returns B if they're
equal, then I'm expecting A to be returned. You know, if A is like more senior memory, right, and then we're going to throw away B, right? Like, there's a subtle difference. You could do it the other way, but I think in terms of performance, it's better to have it match the knock a little bit closer, which would mean that I think we want greater than equal to 0 there. Yeah.
Okay.
Is that?
That's my greater than or equal to. Yeah, my font is a ligature combining. Seems suspicious, huh? Okay.
Yeah.
I really like it for arrows and stuff. It's great. Fira code. All right. So, and then we clear these two and we return our result of our comparison.
I wouldn't call it comp though. I would call it max.
Well, I'm not proud. Let's do it.
So, okay.
All right, let me search greater than
one
more time. Okay, that's it.
No, we didn't. Hold on. No. Scroll up to line 22. Right. So
there's a condition we missed here. Okay.
Right. So this is an optimization, right? This is saying, and this is why we're doing these U3R met checks in the first place, is all just for an optimization, which we could just delete. But it's an interesting optimization, so it's worth describing here, right? So U3R met is measurement, right? Like meter, I think, is why met. That's how I always remember it. So we're measuring, in this case, met 0, which means how many bits. How many bits does it take to represent A? What's the bit width of this number? So if one of these has a bigger bit width than the other, then that one's bigger, right?
Yeah,
we don't need to actually run the. Yeah, I'm a little surprised that checking that is faster than doing the, GMP stuff, but whatever. I guess if you do this GMP stuff, then you have to instantiate a context and all that crap. And so it's like, yeah, if you can do this quick check, if they happen to be small, then it's worth it. That's probably why. That would be my guess.
All right. So, if A is greater than B, return A, else return B. Equal to will not actually. Oh no. We don't want.
I mean, it's either way it will work, but
no, we can't use this. We can't use this actually. because we haven't
Why not?
unpacked the
Wait, why not?
values yet. Oh, okay. I guess we'd have to return.
Yeah, we can. It's the same
We
thing.
can return, but it's A and B, not
Yeah.
C's.
There you
Yeah.
go. I think also we want, yeah, I mean, I would say use greater than, not greater than equal there, because we just checked
Equal.
whether they're equal, right? I don't know, I guess it doesn't matter. It's just that case shouldn't be there, but.
Yeah.
All right, and that is the right direction, right?
It's the same direction we used everywhere else.
Okay, I'm just paranoid about this. I've screwed it up too many times.
Well, let's run it and see, right?
Yeah, let's do it.
Let's make sure that I'm in the right directory here. Okay, so, all right, let's do Basil build Urbit. This might take longer because it's, oh, no. Okay, let's see.
U3WA.
I probably forgot. I probably didn't put this in one of the. Oh, I didn't put it in the header files.
Okay.
You have to add it to Q and H and everything too. Okay.
So it looks like this is alphabetical order. So we went from, yeah.
And W and K. This one is not alphabetical order.
Lame.
It might be the order that it is in the file.
Still lame.
Actually.
The other ones are alphabetical order. This one should be alphabetical order.
The other ones are correct, and this one's wrong. Okay.
Yeah, because there are two of that one and one of this one.
All right, and then
so John High is saying for bit width, I don't think you can use GTE because 17, 18 have the same bit width. Yeah, but there's already a check earlier about like we're only using the bit widths to get the answer if they're actually different. So if they're the same bit width, then we won't enter into that conditional branch. So it doesn't really matter whether we use GTE or GTH, like greater than or greater than equal. Like that doesn't really matter there. I just think it's a little cleaner, but it's not really cleaner to use greater than. I don't know. I think it's arbitrary.
This one's not happy with us using the result of the MPZ comp. So what does MPZ comp return? That's what I got to look up.
Oh, because it returns something that's not a noun. It's probably, yeah, we should look up what it returns. You probably have to cast.
It returns an int, which is +1, 0, or -1. That's all it is. So I don't think there's actually a formally there's not a problem here, or formally there's a problem.
Yeah,
but like, well, this will be.
Wait, is the problem with? I don't think that's the problem. I don't think the problem is with MPZ comp because we're just comparing
with these,
that's greater than or equal to 0. Yeah, so actually max needs to be an MPZ T, not a noun. Right. Or actually what we need to do is just return A or B. So I think max should be a noun, but instead of returning A and P or B and B, we return A and B or B. Yeah.
There we go. Okay.
It's almost as if type safety is a useful feature. Right?
Actually, I'm surprised that this isn't failing on warn all. But
yeah, well, so John, so the other way of writing this check is to say, if A is greater than B, sorry, if AW is greater than BW, then return A. Else, if BW is greater than AW, return B. Else, the bit widths are equal, and then do the MPZ thing. So we could do it that way, but then you'd have to do 2 checks. Whereas I think just checking the negative equality check is probably faster than doing 2 greater than checks. I think. I don't know. Someone who knows about this level of optimization can correct me there.
Okay,
But I think we probably have bigger performance problems than whatever imperfection we have there.
all right. Well, it appears to handle the cases. We could.
Cool. Are we sure that the jet is running? Let's add a tag.
I mean, I always used to just printf
let's
to
add a
make
print.
sure things were running
Yeah,
before.
exactly. That's what I mean. Like add a printf to make sure it's actually running.
Okay.
Just stick it in at the top of u3ka max.
I'm in C, so I need to do that, right? Okay.
I'm not sure. Oh, are you running 140? He says that's a really good question. Well, you can check. You can run.
It's registering
version.
I don't know. So this gets back to the question from earlier. What's the deal with the fact that there's 140 and 139 side by side right now with the jets?
So it's that our jet system in VAR supports running either Hoon 139 or Hoon 140. Those jets are all distinguishable from each other because the knock code is those cores are distinguishable from each other because that Kelvin version is in the core, right? The bottom right tip of every core is the Kelvin version, the Hoon Kelvin. Mm-hmm. So it either says 139 or 140. And so you can check, right? Like the VAR knows which one it's about to run. And so they're actually just two separate trees of jets that describe that this whole stack, right? They're two core stacks, but they share some structure because they're really similar to each other, right? And a lot of the actual jets and even like whole cores or whole batteries are identical, right? So some things change for Hoon 139 and Hoon 140, but not very many. And so the description, like these trees actually have at least some of them are, this are overlap and have the same structure. I don't remember exactly which parts of them. But yeah, I mean, we could have defined them totally separately, duplicated the memory, but it doesn't matter.
Well, now it's not working.
We don't need to.
So I found it. I dropped it down here in 139.1D. And now.
How did you do that? Let me see.
In here, I added the line right there.
I see LTH.
No, that's why. Yes.
You're gonna want to. Okay. You're gonna want to baz n, by the way, at the end of your string there.
Well, for
in the fprintf.
For a quick check, it's. Although it's not showing up.
Nope. Yeah, put baz in there. Let's see. Well, which one of these? Yeah, actually, did we write U3W?
Oh no, there it goes.
What did you just run to get that to happen?
I didn't run anything. It just happened in the background while I was messing around over here.
Happened in the background?
So, okay, so I think two things just happened.
Oh, you didn't have the baz in. Run it again with the baz in. Run again with baz in. I think it's
one of them is that I think that the way that the screen management happens now is not being happy with fprintf to stand error.
I don't know about that. I think it may be right, but okay, there we are.
I don't know where this assertion came from, but normally when I'm working with jets, it means I'm clearing something that I shouldn't be clearing. Yeah.
Clearing, or
like I'm messing up on ref counts is typically what that has meant in the past. But when I'm doing jet stuff,
well, I'm wondering about U3A max here. Is that doing something funny?
This is all crashing right away. Let's see, where's the, well, anyway, the jet is now being invoked.
Is it crashing before? Great. All right. So we've made progress. So we have U3QA max. Are you printing at the very beginning of U3WA max?
Just a second. I got a bunch of core dumps and it filled up my root partition.
The joys of runtime development.
Yeah. Oh, where are you? Okay, there they are. There they are. Oh, sudo.
Yeah, I can't see your screen, by the way. So
yeah, I'm just deleting things in the background,
are.
so I have space again. Okay, all right. Let's see. So back to here. We were getting U3QA max, but it was getting overwritten because the way the terminal is always refreshing in the current version of things.
You might actually need baz r, baz n. I can't remember.
I think I do because it was cutting across, but
right.
But I don't think that's why. I don't think why that's why this is crashing now. This is crashing now because we have something that's off by. I'm
gonna delete that core dump. Yeah.
Yeah, I'll have to delete all these.
So it's doing that before printing, or can we scroll up and see? Is it trying to do a?
No, it's getting deleted, like the output. It was showing up. And then, yeah, here we saw WQ, WQ, WQ. So it was getting invoked for various cases.
So it's making it to Q, but then dying.
It might be hitting one of these cases where something's unexpected.
Well, U3R met is retain, right? Or is it transfer? I think U3R is usually retain.
Takes a pointer and a value.
You're at the wrong function.
Oh, sorry. Yeah.
All right.
Oh, there's a lot of cases here.
Yeah. But I don't see any U3Zs or anything like that. So I think it's safe to say that
and it's not getting cleared explicitly
modifying rep
over
counts
here. Yeah, it's not getting cleared anywhere explicitly over here either. Well, presumably we're hitting this case since the numbers that I was testing with are cats. So this may not be a safe operation for some reason. I don't know why that would not be the case.
I'm wondering if we need to U3K the result, like A or B. I'm not sure. Like in.
Well, okay.
Right.
From
are there any other functions that are like this? Why don't we look at like GTH or something? All right, so this is clearing, but scroll down. I guess it's not returning a noun, so it's a little different.
Yeah, let's
what about
try.
Sub? Let's try sub because that'll return. If B is 0, then we'll return A. Yeah, okay, look at line 22. Right, so we want to, in all the places where we're returning one of these nouns, we want to U3K it, right? Because now there's like the original reference, but also there's this new reference to it, which is like the return value. So I think what's happening here is we've been deleting. Yeah.
And then with max, we actually wanted to U3I and P it too, didn't we? No. Yes,
No, it's just
but
a
we
noun.
did.
We keep
No,
it.
we did, but we
want
wanted
to
to do it
U3K
here.
it. What? Why? Wait, why do we do this?
Oh, no. Never mind. Because it's A or B. It's A or B. We don't have to touch that one at all. We don't have to touch that one.
Yeah. But we do have to U3 max. We have to U3K it. So return U3K of max. I think that's it.
Okay.
Let's try it now.
Okay. Okay.
Yeah, there we go.
All right. I think we're in business. It's
Cool.
super ugly because of the
Because of the prints. We should actually take the prints out now that we know that it's running.
Right. I think that was the only one that was left, and I need to get rid of standard IO. And
all right, it's coming along.
All right, so
let's run it now. Let's just try it with the jet. Do about hint. I think give it 2 big numbers. Well, I guess it doesn't really matter. Yeah.
Right. It'll trigger the 46.
Okay, so this is 46 microseconds, and then
I guess min would be our alternative, because min should have the same logic but not be. Well, although it might be short circuiting. Well, no, it wouldn't short circuit.
Yeah, do min in the other direction. Min in the other direction should be pretty similar, I think.
Yeah, it should be the same.
No, they're the same.
So this might be a case where the jet lookup and everything, jet dispatch and everything is no. It's actually, now I'm getting 25, 27. So okay, so maybe we just haven't run enough cases to know if this is actually worth the.
Yeah, the first one might have done jet registration, perhaps. Okay, so it looks like we're shaving off maybe a couple milliseconds. Wait, we're still printing? We're still printing. Turn off the printing. Printing is slow.
Oh.
Recompile it now that you turn off the printing.
Oh, I did recompile it, but I didn't restart the fake SOD.
Okay. Yeah. There we go.
All right, now we're talking. Okay, there we go.
Yeah.
I mean, they're both pretty fast, but yeah, we are very slightly faster.
Interesting that like min is so much faster too.
Well, I probably
why don't you run it running it 100 times in a row?
Well, I'm also running like video streaming and stuff on the side, so there's going to be a lot of latent drag on my
variability.
CPU.
But try to do col-pal max of Gulf. Wait, does that work? Hold on.
No, you'd have to turn it if you're gonna Gulf it.
Yeah, we could do roll. Why don't we do roll Gulf 1 1,000 max.
All my keyboard shortcuts are captured by VS Code. All right.
Yeah, there you go. Okay, so that took 1 second. No, one millisecond.
One point, yeah.
Yeah, it took 1 millisecond.
Okay, so it looks like we're getting about a 2x speed up.
Not bad.
Okay.
Yeah, note that the speed up is really just in like function call overhead thing, right? Right, because if you look at the Hoon code for max,
Wherever that was. Yeah.
right, that's doing a knock call to greater than, right? At knock 9.
Mhm.
Knock 9s are slow because they're doing all this jet checking and some other stuff, some allocation. So eliding knock 9s is one of the main reasons that we have jets on so much stuff. So for example, all the map and set logic is jetted. And the only reason that's jetted is to avoid the knock function call overhead. So once we have Aries or something similar, hopefully that function call overhead will get knocked out, and then we can remove even more jets.
Yep.
Because we really shouldn't need a jet for max if you look at it, right? Because it should just be we should just need a jet for greater than, which we probably do need a jet for, because that's something that you can get a
Well, we
hardware
had
speed up on.
That's what I copied.
I know, right? So, but I'm saying that we'll probably always need a greater than jet, but we probably won't always need a max jet, because if function calls in knock aren't slow, then this should go just as fast as
yes,
because it should just run the greater than and then return one or the other, and that should be fast enough. Or right, like
right.
it
It's
should
not
be
like
really
we're doing
similar.
like a max operation on a vector that's leading you to really intensive things. So
Yeah.
all
In any
right,
case, this
we
would
did
be
it
cool. We could
live.
make a pull request for this. Maybe we should.
Yeah, maybe I will. Maybe I'll go ahead and implement min too real quick and PR that just for symmetry. I don't know. We could just
How does min work? Like, what's the implementation of min? Scroll down a little.
it's just less than instead.
Yeah.
So, all right. Well, let's. I think we're a little over time for our official limits here, so we should call it a wrap.
I do think we should answer John's question here.
Okay.
He said, but in order to not look up the greater than jet, we have to look up the max jet. Doesn't seem like an improvement unless the function call is also slow when there is no jet. Okay, so let's compare the number of knock function calls for max unjetted versus max jetted, right? So if max unjetted is running, then we have to call, we have to do a knock 9 to run max. And then inside of that max call, we call greater than. So that's 2. And there's a jet lookup check that runs when max is called. Now, if there's no jet, then that check doesn't resolve. We just run the knock. But I think that we always check. So there's some overhead there. And then, but if max is jetted, right, then we run the knock 9 to call max. That does find a jet, and that doesn't cause a second knock 9 to run greater than, right? Because it's just calling the NPZ greater than, or raw C greater than. So it does reduce the knock function calls by 1, from 2 down to 1. And you're saying, I think you kind of guessed this, right? You're saying unless the function call is also slow when there is no jet. I don't know exactly how those compare, but I think they're similar. Like whether there's a jet or not, if you have to check for the jet, I think that I think the overhead is similar. I could be wrong about that, but yeah. In any case, we are seeing an improvement with this, which is cool. So. All right, sorry, Neil, I'll let you close this out.
All right. Thanks for coming on and talking through this. We actually have something to show since we're not using one of the examples of Hoon that is out there. So I'll go ahead and push this. As far as core school goes, it looks something like this, just in-depth discussions of what's going on inside of the kernel as we build this out and some of the logic motivating it. All right. That's a wrap for today.
All right.
So
Well,
we'll
thanks
call
for
that
having me.
done.